This is a laboratory device which allows us to experiment with Hooke's law. It consists of a laboratory stand with a hook at the top, and then there's a coiled spring followed by a weight hanger, a needle arm which you can use to read distance, and then there's a ruler with a reflective backing, and last but not least there's some weights. Each of these stacks of weights consist of 3 10-gram weights, or 30 grams per stack. Let's take a closer look at the various components and how they work together to illustrate Hooke's law. First of all measuring devices need to be properly zeroed. You'll see that this measuring device, when it is unloaded, it reads 0 centimeters on the scale behind it. So this has been properly zeroed. It is possible to move the ruler up or down, so if I was to do that, obviously that would not be a properly zeroed device. But when it works like, now it's going to be a little more difficult to get it back in just the right spot. That, then no weight on the hanger, no additional weight on the hanger, corresponds to 0 distance. 0 load, 0 stretch. That's the starting point for all equations involving a spring. The second thing is to be aware of a possibility called parallax error. And in order to illustrate this point, let me change the angle of the camera a little. All right, let's say you were looking at the image from, at the measuring needle from a high angle like this. From this angle, it looks like the needle is at the, about 0.7, maybe 0.8 centimeter mark. If you go from if you try to read from an angle that's too low, like this, now it starts to look like the measuring needle is above the 0 point, in which case that would indicate that that we're getting either a negative reading, which is kind of hard to do for length, or that the device is improperly zeroed. So how do you know when you've got your head in just the right position? Well, that's where this reflective backing comes in handy. In order to make sure that your perspective, for the average human being not watching this on a video, that would be to make sure that your eyeball is directly in line with the needle, and the needle is directly in line or directly perpendicular to the ruler. You look at not only the needle, but also the reflection of the needle. Let's screw up the parallax a little bit. Okay, if we're off axis, if we are off parallax, you can see not only the needle, but also the reflection of the needle on the mirror. If you get the parallax correct, then the needle covers up its own reflection. So, those are a couple things to bear in mind to make sure that you are both reading correctly and that your instrument has a correct zero. Now, let's get into the actual mathematics, or some, maybe not mathematics, but some measurements surrounding Hooke's law. Right now, 0 load, 0 zero length, or 0 stretch would be the proper term. Okay, I just put 30 grams on the weight hanger, and as you can see, as we move the instrument down, the parallax gets thrown off a little bit, so we gotta move our point of view downwards. And also, we have to wait for this thing to come to a stop. It's still jiggling just a little bit. Let's see if a little bit of damping can help that. By the way, this is why you have to have a table that's very stable. If not, the slight vibrations in the table could throw this off. Alright, so now we're looking at a reading of about, let's see, I would call that 1.55. Looks halfway between the 1.5 and the 1.6 reading. Okay, so again, our measurements so far are 0 load, 0 stretch, 30 grams of load, 1.55 centimeters of stretch. Okay, let's load it up a little bit more. Okay, we're going to put another 30 grams on, so we have a total load now of 60 grams. And again, we have to adjust parallax error because adjust our point of view in order to avoid parallax error. Alright, now we are looking at, this thing's still bouncing up and down. Regardless, we know that our load is 60 grams. And let's see if we can slow that up and down motion down a little bit. There we go, that's a little more stable. And to me, this looks like 3.05 centimeters. Again, it's looks to me like the needle is halfway between the 3.00 mark and the 3.10 mark. So we'll call that 3.05. Let's put another 30 grams on. Oops, dropped 10 grams. All right, here we go. It's coming back. Okay, we're back. We got the extra 10 grams back on there. So total load is 90 grams. And we are looking at a distance of, let's take a closer look at that. If you try to correct for parallax as best you can. Looks like 4.60 centimeters. 4.60 centimeters. All right, last thing we're going to try here is to put another 30 grams onto this. And again, we got to slow the thing down. Even a millimeter of up and down motion could cause a error in measurement. And we have to adjust for parallax error. Notice that the needle is not overlapping its own reflection, so let's move down a little bit. Alright, that's pretty good. Alright, so now we are looking at a load of 120 grams and a stretch of, let's see, that is the 6.0 mark, and so it looks like we're just 1 millimeter below it, so call that 6.10 centimeters. So once again, our 5 data points are, when we zeroed it, we said 0 load, 0 stretch. When we put on 30 grams, we got 1.55 centimeters of stretch. When we got 60 grams on there, we recorded a distance of 3.05 centimeters, a stretch of 3.05 centimeters. When we had 90 grams on there, we had a stretch of 4.60 centimeters, and when we had 120 grams of load, we had 6.10 centimeters of stretch. All right, now let's talk about the theory behind all this, otherwise known as Hooke's law.